what I want to look at now is I want to come up with some differentiation formulas. And differentiation, that's another term that means derivative. Differentiation formulas means formulas for finding the derivative. So differentiation, if you see that word, that's another word for derivative, okay? But the good news is there are some formulas that will allow us to find derivatives much quicker than using our definition of derivative, which, let me write that up here. The definition of derivative, it's in a lot of cases, that's a tedious process. The derivative is f prime of x equals the limit as h approaches 0, f of x plus h minus f of x over h. Yeah, that you can run into a lot of things. You got to sometimes use the conjugate, you got to use factoring, a lot of different things you can run into. So it can get complicated, I guess, another way to say it. But the good news is there are some formulas that will allow us to do these derivatives much, much quicker. They're really nice. But let's talk about it. All right. So I got on the handout here. I'm starting off on number 1 on the handout. Suppose C is a constant, any constant whatsoever. So using that Leibniz notation we just talked about. So this is asking d dx of C. So what I'm asking for, what this notation here is good for is this is saying, so if I've got f of x equals a constant, f prime of x, what is it? So all of that is summarized right here. So that's the nice thing about using this Leibniz notation. You can say all this with that little notation here. But anyway, so what is the derivative of the constant? Well, I am going to go through this with the definition of derivative, but then we're going to notice some patterns here. And this one's really nice because, so the derivative, so over here, so I'm using, instead of f prime of x, I'm saying, what's the d dx of f of x? So this is my f of x, the C is. All right, well, it's the limit as h approaches 0. Now, f of x plus h, well, my f of x is C, so plug in x plus h, well, I plug in x plus h for x. There's no x, it's just a constant, it's just a number. And so f of x plus h is C. F of x is C, divide that by h, you got 0. Yeah, the top number is just 0. It doesn't really matter what the bottom is. The top number is just 0, so this derivative is 0. Anytime you have a constant, so here's what this is saying. Anytime you have f of x equals 5, the derivative is 0. If x is 15, the derivative is 0. If f of x is 150, the derivative is 0. That's what this is saying. Anytime you have a constant, if this number is a constant, the derivative is 0. All right? So that's our first formula, if you would. If you got a constant, the derivative is 0. Okay? Maybe I should write it in words. Be better. The derivative of a constant is 0. Always 0. All right. That's first one. All right, so number 2, I do the same thing, d dx of x. All right, so yeah, if I plug in, got this all written out for you, but I'll write it up here. All right, so if I do the limit definition, this is my f of x. So if I plug in f of x plus h, so it'll be x plus h. If I plug in the x plus h for x, it'll be x plus h minus f of x. Well, the f of x is x over h. That's what I got written down there. So what happens? Well, the x's cancel. We get h over h, which is 1. The limit as h approaches 0 of 1 is 1. So the derivative with respect to x of x is 1. Okay. Not much there, but that's what it is. All right. Number 3. is x squared, ddx of x squared. Well, we've got this all written, so it's limit as h approaches 0. Yeah, so my f of x is x squared, so it'd be x plus h squared minus x squared over h. Well, you fold that out, you got the limit as h approaches 0. X squared plus 2xh plus h squared is what you get if you square that out. Then minus your x squared over h. All right, so this is where you tell me what happens then when I've got all that, because all that's on the handout. What happens? X squared minus x squared leaves me those two. Common factor of h. Factor that off. Cancel the h. Plug in h to be 0, right? That's 2x. The h is 0, so that's just 2x. All right, number 4. Actually, I've got these through x to the 4th. But it's all good because it really pays off nicely here. Yeah, and that's all right. So if I do ddx of x cubed, that's my f of x. So f of x plus h would be x plus h cubed minus x cubed divided by h. If I FOIL all that out, you know what I'm saying? Multiply all that out. I've got done for us here. So it's x cubed plus 3x squared h plus 3xh squared plus h squared h cubed minus, so all that's x plus h cubed, but then I have the minus x cubed over h. Done all that ahead of time here. So look at that. The x cubes cancel, and we're left with these three, but those three all have a common factor of h, so if I factor that h off, I get h times 3x squared plus 3xh plus h squared. Then the h's cancel. Now I can do h is 0. Well, that will make that 0 and that 0, so all that's left is 3x squared, isn't it? So it turns out the derivative of x cubed is 3x squared. All right, one more. Then we'll look at the pattern. ddx of x to the 4th. We've got the limit as h approaches 0. Well, now it's x plus x to the 4th, so it'd be x plus h to the 4th minus, so that's f of x plus h minus the f of x would be minus x to the 4th over h. All right, so if I multiply all that out, I got it on the paper, it's x to the 4th plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the 4th. So all that's x plus h to the 4th, and then minus the x to the 4th divided by h. Yeah, that, I mean, if you don't know the little rule there, that takes a while. But, so it pays off. It'll pay off here. What happens? Same thing, x to the 4th minus x to the 4th. Those are gone. What's left? Well, we got 4 things left. But they all have h in them, don't they? So I can factor off an h. So limit then of h goes to 0. So it'll be 4x cubed. Factor off the h, so it'll be h times, parentheses, 4x cubed plus, take an h off there, it'll be 6x squared h. Take an h off there, it'll be h squared, so it'll be 4xh squared. H off of that will be h cubed. Well, the h's cancel again. H goes to 0, so that's 0, that's 0, that's 0. All that's left is 4x cubed. All right, so ddx of x to the 4th is 4x cubed. All right, so there's a pattern here, and if you know it already, don't let it out. But let's notice here, specifically on these three, and then we'll talk about the other. All right, so if we've got x squared, the derivative is 2x. If we've got x cubed, the derivative is 3x squared. And then the derivative of x to the fourth is 4x cubed, based on the definition here. What's the pattern? Well, if you just look at the power, what happened to the power? That's 1 power, that's 2 power, that's 3 power. The power did what? It went down by 1, didn't it? So when I do the derivative of just a x to a power, a variable to a power, the power decreases by 1. So you're going to subtract 1 to get the new power. Where did this number come from? Well, if you notice those numbers, that's exactly what the old power was. So we just kind of brought that one out, didn't we? That's not coincidence. That's how that worked. Yeah, the number in the front is what the old power was. So you just bring the old power to the front and then make the new power 1 less. That's the pattern. So that's our derivative power rule there, we call it. If you're doing the derivative with respect to x of x to the nth power, any power of x, doesn't matter, turns out, it's going to be, you're going to bring the old power down and then multiply by x to a new power, and the new power is, what do we say, subtract 1, so it's going to be n minus 1 power, if we write it kind of in general. That's going to make this a whole lot easier, isn't it? Because you can see we got to x to the fourth here. X to the fifth is going to be longer. And those powers just make things longer. And then that was just a simple x to a power. What happens to the others? Well, I'll talk about that. So, use this newfound power rule. Let's skip the, how about we skip the definition stuff and let's use this if we can, right? Okay with that. All right, so try it on these. All right, so if we've got f of x equals x to the 7th, we'll go back to a regular. Notation here. What's our derivative? Well, by the power rule, instead of having to go through that whole limit definition, power rules tells me bring down the power. New power is 1 less, so it'll be 7x to the 6th. That's going to be a whole lot quicker, isn't it? 7x to the 6th, that's going to be the derivative. G of x, let's say, is x to the negative 5. Well, we did these with positive powers. All these. Good news is it works on negative powers too. G prime of x, bring down the power. Now the only thing you have to be careful with, this new power is 1 less. It's negative 5 minus 1. So the new power is not negative 4. What is it? Negative 5 minus 1? Negative 6. Yeah, just have to be careful of those negative powers. You're subtracting 1, so it goes down to negative 6. It also works on square roots. All right, so square root of t. That's not written as t to a power, but can't I write square root of t as a t to a power? What is t to what power is the square root of x? Anybody know? 1/2? Yeah, the square root of t is t to the 1/2. And so if I write it as a power, the derivative is so very easy. Just bring down the power, 1/2, and then the new power, t to the new power. What would the new power be? 1/2 minus 1. Just have to do a little fraction, subtraction there, but it's negative 1/2, isn't it? I would imagine if we did that, that one using the definition would get rid of that conjugate. Probably have to do the conjugate thing. We don't have to now if we're allowed to use this rule, which, so the deal is on the test, you'll have to use the definition on some of these, but unless I say you don't have to use the definition anymore. So y equals, let's talk about this one. All right, so that's the square root. What about the cube root? Same deal. Instead of square root, we got a cube root. So what's the cube root? Well, the deal is the root tells you the power, or the denominator of the power. Cube root is 1/3 power. Like this is square root, so there's root 2. We don't write 2 there, but that's a root 2 radical. This is root 3, so that tells you the denominator. So if it was 4th root, it would be 1/4. 5th root would be 1/5. That's how that works. FYI, in case you didn't know. All right. So then the derivative, it's easy now. It's just power. We'll bring down the power, subtract 1, get the new power. 1/3 minus 1, negative 2/3. Squeezing a bunch of them in here. All right. S of P. Yeah, I mean, it works the same for any variables we want to. S of P is 1 over p to the 9. Now we have to be careful with this one, because the power here is not, for the power rule, is not 9. The reason we can't use the power rule as is right here is because I needed an x to a power form. This is 1 over something to a power. I don't need that. I need to rewrite it as p to a power. I don't need it 1 over. See what I'm saying? What power of p is 1 over p to the 9th? It's negative 9, right? It's a negative exponent. So this one's like the second one I've got there. Yeah, so just rewrite that 1 over p to the 9th as p to the negative 9. Then your derivative, very simple. Bring down the power. The new power, subtract 1. What's the new power? Negative 10. Okay. F of x equals 50. Just bring this one up again. What do you got for derivative there? Well, that's going back to the very top thing we talked about, right? The derivative of a constant is always 0. Yeah. If you don't have a variable, the derivative is 0. Okay. So those were the basics there of what that gave me. All right, now. On the handout there, at the very bottom, all right. So at the bottom of the handout, I said, what about blank? What about 4x to the 6th ddx of 4x to the 6th? Well, my little notice says, well, let's think about what happens here. And just write it up here. So I've got the ddx. So I've got, basically what I've got is I've got a So if I do my limit definition, you got x plus h to the nth minus c times x to the nth, because that's my f of x. So f of x plus h would be x plus h to the nth. F of x is c x to the nth over h. That turns into, factor out the c. So we got the limit as h approaches 0, factor out the c, so I have x plus h to the nth minus x to the nth over h. Well, we talked about limit stuff, a long time ago, but basically one of the rules in limits is if I've got a constant times something, I can bring that constant out. So you can wind up with constant times the limit as h approaches 0, x plus, I don't remember which number rule that one was, but remember we talked about those limit laws, limit law 1, limit law 2. I made you do a couple of them on the homework, but that was one of the limit laws. I can bring that constant out. And what happens is, this then turns into, this right here, that's the derivative of x to the n. If you think about it, that's what the derivative with respect to x of x to the nth would be, because it's x plus h to the n. And we know what that is, right? That's the power rule. So it's c times, bring down the power, x to the new power. So the point of all this is, what happens when I have a constant times an x to an nth power? You just bring down the constant and multiply it, bring down the power and multiply by the constant. I.e., ddx of 4x to the 6th, I'm just going to take the 4, bring down the 6 and multiply it by the 4, and then make it new power x to the 5th. Yeah, you're just going to wind up multiplying the 6 times the 4, 24. Okay, so it's very nice, very nice. Okay, so f of x equals for x cubed, the derivative would be then what? Well, I'm just going to bring down the power and multiply by the 4, so it'd be 12, and then make the new power x squared. So that really doesn't complicate it much at all. You just have to multiply that number you bring down, just have to multiply it by the power there. All right, now here's the next step. On the back page of the handout, I'm not going to write all this up here, but if I go through the definition of and use with addition, so I've got a function, and it's a combination of two functions, if you will, two things added together. Good news is that, like I said on the handout there on the back side or the second page, I've got it all worked out using the limit definition. Turns out, just doing some rearranging and stuff like that, f of x plus h and g of x plus h, rearranging, got it all there. Turns out, if you go through all that, what you find out is the y prime equals f prime plus g prime, basically, just said. Which means, all I have to do if I've got addition is do the derivative of that, and then add it to the derivative of that. It's very nice. Very nice. And then at the bottom of that page, f equals f minus g, so if we got subtraction, gone through the whole thing, but long story short is the derivative, you do the derivative of f minus the derivative of g. Which may seem like, yeah, okay. You can't do that with every operation. And I'll show you what happens with multiplication. You can't do it with multiplication. You can't do it with division. You can do it only, this only works for addition and subtraction. So it is significant what that result, because it doesn't work for every operation. But what this means is, when I have now this, so I've got y equals x squared minus 9x plus 8. Let's do this one. Sorry. I think that one's for next time. All right. If I have y equals 7x to the fourth plus 9x squared minus 8. Well, I got plus, I got minus, plus and minus. We just do the individual derivatives and put them together. So the derivative here, I can just do the derivative of that. What's the derivative of that? 4 times 7, 28. New power, 1 less, x to the third. Yep. Get rid of that then. This is addition. Bring down the power. 2 times 9 is 18. New power, x to the first. And then that's a constant. Derivative of that is 0. Derivative constant is 0, so there's nothing. You don't have to write that. That's it. So anytime you have additions and subtractions like that, you just do them individually. Okay? I did want to mention okay. So addition and subtractions, yeah, you just do those individually. I'll mention it next time too, but here's the kicker. You've got y equals f times g, so I've got two things multiplied together. Turns out, the derivative, and we'll talk about it more next time, the derivative is not, unfortunately, f prime times g prime. So so these are really nice. It doesn't always work. If you have multiplication, that little thing doesn't work. You can't do the derivative of this times the derivative of that. And I'll show you more about that more later on. And then y equals f divided by g. Turns out the derivative is not f prime divided by g prime, unfortunately. And we'll talk about, if we have to go to a formula, if you will, what those are. But for right now, just know you can't do it as nicely as the plus and the minus. So those are really nice. It doesn't always work on all operations. So so the one thing I would say here, so what do we do? Well, there is a rule for each of those, and we'll talk about those next time. But in the interim here, there are some things we can do, like if I have y equals (3x), let's say, times x squared plus 4x minus 5. That's times. That's times. And trust me on this, we can't do the derivative of that times the derivative of that. I can't do the derivative of that times the derivative of that. It just won't work. So what can I do? Well, what I can do here, if it's possible, is get rid of the times. Distribute here. If I can distribute, I'm trying to find the derivative. If I can distribute, if it's written, multiply it out, you know, the derivative of that as is not easy. So if I can distribute it out, get rid of the times, that's what I'm going to do. So just distribute that and make it y equals, what would that be, 3x cubed plus 12x squared minus 15x. That gets rid of the problem. Now it's just this plus this minus that. And I can do the derivative individually of just pluses and minuses, you see. It's just the times that was throwing it off. So what's the derivative? Well, it'll be 9x squared plus 24x. Now, we haven't done one quite like that. What's going to happen there? That's not a constant, but what happens? What's the power here? You think of it that way. It's 1 power, isn't it? So if I bring down the 1 power, it's still negative 15. And what's the new power? X to the 0? But what's x to the 0? 1. So yeah, if it's just x to the 1, the x kind of just drops off. See what I'm saying? Yeah. So if you got times and you get rid of it by distributing or multiplying, foiling, something like that, then that takes care of that times problem. Because you can't do derivative times derivative. Well, what about the divide? If you can, here's something you can do. If you got divide, say I had y equals five x cubed minus 40. Let's divide that by 5x squared. 5x cubed minus 40 divided by 5x squared, okay. Well, divide, you can't do the derivative divided by derivative. It just doesn't work that way, unfortunately. What can we do? Well, something similar, I guess. It's probably not as, probably something we're not as used to as distributing there, but this 5x squared, one thing I can do is just think of it, I can divide both of those by 5x squared, 5x cubed divided by 5x squared, and then minus 40 divided by 5x squared. I can do that and get 5's cancel. This would just be x, and then this would be minus, well, only the 5's cancel, so that would be 8 over x squared, which I could write as 8x to the minus 2. With me there? Now I can do the derivative, because now it's just subtraction, isn't it? I don't have division anymore. So the derivative is, what's the derivative of x? It's not 0, it's not a constant. Power is 1, so I bring down the power. And what's the new power? X to the 0? Yeah, so it's just derivative is 1 of x. Here, bring down the powers to be plus 16, x to the, subtract 1, what's the power? Negative 2 minus 1 is negative 3. So that's how sometimes you can do division. Sometimes you won't be able to do quite that. So we'll talk about that more later on. Any questions on that?